Okay, ladies and gentlemen, welcome back. We've got today's lesson, and today's lesson is writing net ionic equations, and I have it up here. Writing net ionic equations. And this is kind of going to be kind of a step beyond the balancing equations that we did. So we're going to be going ahead and doing that today. But first off, before we find out how to write out net ionic equations, balance net ionic equations, we got to know what they are and you know, why would we would use them? Okay, so let's go ahead. Start off with a PowerPoint right here, and this PowerPoint right here is basically just going to start off by going over and reminding ourselves what does it mean to be aqueous? What does that AQ mean? So if you look at this right here, you see that we saw this in yesterday's lesson, and so this is where we're picking up or actually reviewing a little bit. If something is aqueous, it means it's broken up into its ions. At least the ionic substances are. There's molecular substances that are aqueous. That just means they're broken up into their individual molecules. But as ions are concerned, we break them up into their individual ions. So sodium chloride breaks up into sodium ions and chloride ions. And here I have a visualization for you here, right? So the sodium ions are by themselves, the chloride ions are by themselves. And remember that ionic compounds come in what we call empirical formulas, which means they tell you the ratio of one ion to the other. They don't tell you exactly how many ions there are in a crystal. They just give you a ratio. So a one-to-one subscripts here means that for every sodium, there's a chloride. Okay. Same thing here. Potassium bromide aqueous means there's potassium ions and there's bromide ions. They're all kind of set apart from each other, and they individually move and slide past each other. Okay. Remember, these ions that I'm drawing are like gazillions of times way too big. They're not that big in real solutions. They're really really small. And I don't know if you remember from last time, but the word solution means a mixture of stuff, a really good mixture of stuff. And we'll get into details and definitions of that in chapter 15, but not right now. Potassium sulfate, when it's aqueous, it is sulfate ions. SO4 is a polyatomic ion, and potassium ions. Remember, we talked about this yesterday. Not all subscripts are created equal. Some subscripts are part of a polyatomic ion. Some subscripts are there because of the charge and the number of ions that have to be on these ions to make the ionic compound equal to each other. Right? So in this case, potassium sulfate, when it ionizes, it forms two separate potassium ions because potassium is in column 1 in the periodic table, and it gets a plus 1 charge. So since sulfate is a -2 ion, we need two separate potassium ions. So the 2 subscript on the potassium is telling you that you need two potassium ions. Normally I'd put a 2 in front, but I want to show here that they're two separate potassium ions. And the sulfate here is, that's the formula. SO4 is the formula for the sulfate ion. So this 4 right here does not behave like the 2. The 4 here is for a different reason. They're both still telling you how many potassiums and how many sulfates there are, oxygens there are. But these 4 oxygens are part of one sulfate ion. So that sulfate ion requires those 4 oxygens, so we don't bring it out to the front like we would with the potassium. So it's important to know what the formulas are for the polyatomic ions, because then you'll know, whether these subscripts are part of the formula for the polyatomic ion, or they're subscripts just telling you how many of that ion there are for the with respect to the other ion. Right. So here there's 2 potassiums for every 1 sulfate. That's the purpose of the 2. The purpose of the 4 here is part of the full formula of sulfate. And here you can see, once again, I've got the potassiums and the sulfates. You'll notice there's twice as many potassiums as sulfates here, because that's what that 2 subscript is for the potassium, as we've said. All right, so we've done some balancing of chemical equations. And when you do balancing of chemical equations, you're going to balance all kinds of different stuff. Make sure that you've got the same number of atoms on both sides. But sometimes chemical equations can be a little bit misleading or deceiving. Let's say we have a chemical reaction that says that lead nitrate uh, plus potassium iodide forms lead iodide plus potassium nitrate. Okay, and so what you're basically saying is, I got this substance here, lead nitrate, and I'm mixing it with potassium iodide. Well, I've got potassium iodide also. When I mix the two, there's double a double replacement reaction occurring, and the ions are being exchanged. So the lead here goes with the iodine here, forming lead iodide, and then the potassium here goes with the nitrate here, forming the potassium nitrate. So it looks like we made two products, right? But you know, I guess the second product really we never see it. You'll notice that the second product here is aqueous. The first one is a solid, and we've seen this on videos where we mix the two clear solutions, the two clear liquids, and you get this yellow stuff that's forming. That's the lead iodide. Okay, so we've actually seen samples of that. Um, so really, what's happening here is we're forming a solid, but we're also forming aqueous potassium nitrate. Not to say that it's not there, but it's just probably not as interesting. So let's see what happens here. I've got some figures drawn down here. So this lead nitrate solution over here, the first one, it looks like this. Right? You get your lead ions and your nitrate ions, and once again, the second, the polyatomic ion here is in parentheses. It has a 2. It means that there's 2 nitrates for every lead ion, because the lead is a +2. This is lead 2 nitrate. The second the second solution here is potassium iodide, Ki. And so here I've got potassiums and iodides. Because the subscript for both potassium and iodide are both 1, that means there's a 1-to-1 ratio. And here I'm showing 2-to-2, which is the same ratio. Um, I don't have to draw it. Just 1 and 1. I can draw. As long as I've got the same number of potassiums as iodides, they're in the same proportion, then that would be fine. If I drew 100 potassiums and 100 iodides, that would be correct. Because really, there's like a gajillion potassiums and gajillion iodides. So these are the solutions we have before we start this reaction, before we start this double displacement reaction. Once we get them and we mix them, what happens is this. We form lead iodide and potassium nitrate. So the lead iodide is basically a solid, which means that the lead iodide is going to kind of get together, and all the lead iodide particles are going to not become ions anymore. They're going to become an ionic solid. They're not individual ions. They're trying to get together in a crystal lattice like we've talked about before. So eventually, the lead iodide is going to form within the solution. And eventually, because it's a solid and it's not dissolved in water, it's going to drop to the bottom. That's why I've drawn these all the way to the bottom. So if you ever do that little experiment where you got the two clear liquids put together, you get that yellow mixture that you get. If you leave it overnight, in the morning, all that yellow is just like a small little layer at the bottom. It's all the solid that's come out. And the rest of the mixture is clear. I know, because I've done it many times, but we can't have it here. The rest of the solution is the potassium nitrate. The potassium nitrate is still aqueous. But the potassium nitrate is still going to be, potassium ions are going to be floating around, the nitrate ions are going to be floating around. It's still going to be aqueous. So if you look at this reaction, think about it. The potassium and the nitrate really didn't do anything. I mean, let's compare. If you go back to the beginning, there was nitrate floating around by itself, right? It's in there floating around with a lead, right? But it's floating around by itself. All the nitrate ions are by themselves. And so are the potassium ions in this other solution. So potassium is floating around by itself to begin with, and so is nitrate. That's how they began. So were the lead and the iodide, because both these solutions are aqueous. They're soluble in water. Once we mixed them, the lead ions and the iodide ions, well, they got together. They got together, and eventually they floated down to the bottom. But the potassium and nitrate are still floating around by themselves. They haven't got together. They haven't hooked up, right? They're just kind of by themselves there. So, really, the potassium it's like when people go to dance. There's some people get to dance, and some people dance, and some people stay on the sideline. We call them wallflowers. They just kind of stay on the side and don't dance with anybody. Well, that's what these guys are. They're kind of like the wallflowers. They don't dance, and we call them spectator ions because they were just kind of hanging around. They were watching what was happening, but they didn't do it. The lead and the iodide were the ones that kind of got together. And on Monday when you go back to school after a dance on Friday night, well, everybody starts talking about who danced with who, right? Or who started talking to who, or whatever happened. That's the news. The people that stood there against the wall of the gym, nobody talks about them, right? So these guys are the spectator ions. So what we care about in our net ionic equations is, tell us what interesting thing happened. Tell us what new stuff was for. Tell us what's just not floating around, that was floating around before and is still floating around. Tell us what else happened. And basically, the way that what's interesting here is when something is formed that is a solid, liquid, or gas. Okay, basically, solid, liquids, or gases are what we're considering something new and interesting. So, in order to describe this, you make your net ionic equations. And this next slide, this last slide here, basically is going to give us the 4 steps that we have to do in order to balance our net ionic equations. Step 1 is to balance the chemical equation that you've got. So everything has to be balanced. You can do it later, but it becomes harder. So it's easier if you just balance the equation at first. Once you got the equation balanced, you break up all the AQ substances, all the aqueous substances, into their ions. So whatever sticks around breaks up into ions. Whatever's aqueous breaks up into ions. Sometimes, like in this case, you're going to find that there are substances that were ions to begin with and ions at the end. So you're going to end up with ions on the left side of the equation and ions on the right side of the equation. So you'll figure that, you'll see that. And what you do is you cancel them out. You cancel out the spectator ions. I'll show you right now when we do a sample problem. Once you cancel out the spectator ions, you write out the equation with all the species that are left over. And then you're done. All right. Step 1, balance the equation. Step 2, breaking up all the aqueous substances into ions, including the right number of ions. You cancel out the spectator ions. In other words, the ions when they appear on both sides of the equation. And at the end, then you write out an equation with the species that are left, whatever is left over. Okay, so let's go ahead and give that a shot. So we've got a few sample problems here. Let's do this one first. This one's easier. Hopefully this is not too, I hope it's not too sloppy. My writing here, once again, I think it's better on a chalkboard, but still. All right, so step 1 said, first off, let's take a look at this chemical equation. This chemical equation right here says calcium chloride, which is aqueous, reacts with sodium carbonate, which is also aqueous. Just like we saw that last example. And it forms calcium carbonate, which is solid, plus sodium chloride, which is, it should be aqueous. Let me fix that real quick. I don't want to start this video from the beginning. If that remained solid, then this would be a very uninteresting and also very inaccurate problem. All right, so this is aqueous, aqueous, aqueous. First step, though, before we worry about what's aqueous and what is not, we want to go ahead and balance the equation. So there's a calcium here, that's balanced. 2 chlorines here, 1 chlorine over here. So in order to balance the chlorines, we need to put a 2 in front of this one. This one's an easy one to balance, watch. So now we've got 2 chlorines on both sides. That's balanced. 2 sodiums here, along with 2 sodiums here, because of the 2. Now the sodiums are balanced. And there's a carbon here and a carbon here. and then 3 oxygens and 3 oxygens, right? One carbonate, basically, on both sides. So step one, balanced. Go back here. Step one, balanced chemical equation. Step two, break up all aqueous substances into their ions. So now we're going to have to go back here, and hopefully we'll have enough space here. Now we'll use 2 rows. We got to break up all these aqueous substances. Aqueous. This one, this one, this one. We got to break them up into their ions. So let's see how we break them up. Remember, we did this work, this assignment yesterday. Or at least that was the assignment. Calcium chloride, 2 ions right here. Calcium ion, and calcium is in column 2. So you get a +2. Remember, you go on the periodic table to see what the charge is. See what row they're in, what column they're in. Sorry, column, not row, to get the charge. Now, chloride is a -1 ion. It's in column 17, but there's 2 of them. So we're going to write this as 2Cl. Okay, so this is just like that worksheet the other day. Calcium chloride breaks up into calcium ion and 2 chloride ions. Once again, that 2 is to give the ratio there. Sodium carbonate is made up of 2 sodiums. Remember that carbonate here, if we went back to this polyatomic ions, carbonate is right here. It's got a -2 charge on it. So that means that sodium is in column 1. It gets a +1 charge. And there's 2 sodiums there and 1 carbonate with a -2 charge on it. And remember, this 2 comes from that subscript 2 right there. Because remember, this 2 here was because we needed 2 +1s to balance out the 1 - 2 on the carbonate. Now, this one right here, calcium carbonate, is a solid. We don't do anything to it. Just write it out as calcium carbonate. Rewrite that. Notice I'm not putting the states of matter right now. You can, but it's really not necessary. And then in the end, we're going to go ahead and write out, the last one is sodium chloride's aqueous, and there's 2 of them. So from 2 sodium chlorides, we get 2 sodium ions and 2 chloride ions, plus 2 chloride ions. Okay. Some people go, where did I get 2 here and 2 here? Well, these were 2 NaCl's. Each NaCl has 1 Na and 1 Cl. So if you have 2 NaCl's, you would have two Nas and 2 Cl's. Right? It's kind of like if you had 2 hot dogs. Let's say a hot dog was, a bun and a wiener, right? So if you had 2 hot dogs, you would have 2 buns and 2 wieners. So same thing with here. So if there's a 2 in front of here, it means there's 2 sodiums and 2 chlorides. So when you break them up, you end up with 2 sodium ions and 2 chloride ions. So that's step 2. All I did was take the calcium chloride here, break it up into its ions, just like the worksheet from the day before. The sodium carbonate, broke it up into its ions, 2 sodiums and 1 carbonate. And the sodium chlorides, broken up into their ions, sodium and chloride. Go ahead and show how they're broken up. Remember, the first element, it's a metal, it's by itself, an ion. And since there was 2 of them, I put a 2 in front of each of these guys. Okay. So that's step 2. I'm going a little slow right here. They go a little faster, but to show you kind of how this works, I'm going a little slow right here. Back to here. Step 3, cancel out spectator ions. So now we're going to go ahead and cancel out spectator ions. So going back to our problem, where the spectator ions are the ones that appear on both sides. So you'll notice here that there's a calcium ion here. Now there's a calcium here, but it's not a calcium ion by itself. It's part of the calcium carbonate. So we don't consider that the same thing. But there are 2 chlorides over here and 2 chlorides over here. And there are 2 sodiums over here and 2 sodiums over here. Okay, so since it's kind of like in math class where if you had like a x plus 8 equals to x plus y, you can get rid of x. You can subtract x on both sides, and they would cancel out. Cancel that out, cancel that one, and then you're left with just whatever is left. Same thing here. So there's a 2Cl here, cancels out with a 2Cl here, and two sodium ions here, cancel out with two sodium ions there. So those guys cancel. That's step three. Okay. So step one was to balance the equation. Step two was to take all the aqueous substances and break them up into their ions. The ions that you find on both sides of the arrow, both sides of the equation, are the spectator ions. So step three is to cancel them out. Which brings us to the last step. Just to remind you here, you write out the equation with whatever's left over, and we're going to go ahead and do that. And so what's left over is the calcium ion and the carbonate ion on the left-hand side goes to form. The only thing that's left here is calcium carbonate. And that's it. All right. This is your net ionic equation. Okay. And what this tells you is really what was formed. What you ended up with, and if I put states of matter, I can put the states of matter here. I can go back to the original. This calcium carbonate was always solid, so it remains solid. And this carbonate came from sodium carbonate, which was aqueous, so it'll remain aqueous. And the calcium ion here came from the calcium chloride, which was also aqueous. Ions are almost always aqueous. A few exceptions, but almost always aqueous when they're in their ion form. So this thing is saying is the only really thing that happened here was that calcium ion reacted with carbonate ion to form calcium carbonate. Yes, there was some sodium in there was some chloride, but in the end, look, sodium ions were by themselves, chloride ions were by themselves, and in the end, sodium ions remained floating by themselves, and so did the chlorides. So that's why we canceled them out. There was nothing interesting. We started with some calcium ions floating by themselves and some carbonates. When we put the two together, they formed calcium carbonate. That's what we were interested in. Okay. So that's how you write a balanced net ionic equation. Once again, it's a net ionic equation. And when I use the term net, it means, once you take it into account everything. Okay. I don't know how many of you ever picked up a paycheck. You work and actually, get a paycheck. But there's a thing called gross pay and net pay. And what you get is the net pay. So, let's say you're getting paid $10 an hour for 20 hours. 20 hours times $10 per hour is $200. So your gross pay, how much you got paid total, is $200. 20 times 10 gives you 200. But then comes the state tax and the federal tax from the U.S. government. They take out money, and then the money to pay your health care benefits, and then they take out money for union dues, and then they take out money for social security, so that when you're over 65, uh, you'll end up having some money that you can get. They take out all these little funds little by little. So you might have been paid $200, but what you're going to end up getting is 200 minus all those other things. And they all calculate different rates. You might end up with, let's say, $170. So instead of $200, once you add up all the stuff they take out $30, and you end up with 170. That's your net pay. That's what you actually got, right? Gross pay was like what you're supposed to get, but net pay is like, okay, well, the reality is you have to give up some part of your paycheck for taxes and for your health care benefits and stuff like that. So the net is really the real world, what actually happens. And here, the net ionic equation is that calcium ions and carbonate ions are getting together to form calcium carbonate. There's no sodium chloride formed. If you take that solution that's left over, it'll be salty. There'll be sodium chloride in there yet. But sodium chloride itself was not formed. It's sodium chloride, aqueous sodium chloride was formed. In other words, there's sodium chloride still floating around, but the sodium never got together with the chloride. Okay. Let's try one more problem. Okay. Let's try the second problem here. All right. So this one's a little bit trickier, only because the balancing is a little more involved, but it's still the same 4 steps. So we got aluminum nitrate. That reacts with lithium hydroxide, both aqueous. It's going to form lithium nitrate, which is aqueous, and aluminum hydroxide, which is a solid. I don't know what I was thinking when I put these problems together earlier. I'm having trouble with my pen here. Okay, very good. I'm hoping. There we go. All right, now we can go ahead and do this. All right, step 1, let's balance this equation. There's 1 aluminum here, 1 aluminum here. There's 3 nitrates here, and thank goodness for the parentheses. It lets me know, hey, NO3 is a polyatomic ion. So there's 3 of them here, and if you look closely, you can see that there's an NO3 over here. But there's only 1 of them. So there's 3 of them on this side. There's only 1 of them here, so I think I'm going to need 3 of these guys right here. I'll put a 3 here to have 3 nitrates. Now my nitrates are balanced. Now I've got 1 lithium here, and I've got 3 lithiums over here, so I need to put a 3 in front of here to balance out the lithiums. Oh, and when I do, notice, I put a 3 in front of here, it balances out the lithiums, and it also gives me 3 hydroxides. And guess what? On this side over here, I have 3 hydroxides. Once again, the parentheses tell me, hey, there's a hydroxide, there's a polyatomic ion in the parentheses. It's hydroxide. And if you recall, hydroxide it's got to be over here. There it is. Kind of 2/3 of the way down. That's a polyatomic ion, OH, with 1 negative charge. Okay. And so now my equation is balanced. Put a 3 here, put a 3 here, it's balanced. Step 1. Step 2, break up the aqueous substances, this one, this one, this one, break them all up into their ions. So this one right here, I've got 1 aluminum and 3 nitrates. So I'll break it up into aluminum ion. And if I look at the periodic table, aluminum is in column 13, so it gets a +3 charge. That's why I need my 3 nitrates. If you look at this table right here, if you look at nitrate right here, nitrate has a -1 charge. That's why we have 3 nitrates. So when we break them up, there's going to be 3 separate nitrates. 3 separate nitrates floating around. So aluminum nitrate breaks up into aluminum ion and 3 nitrate ions. Lithium hydroxide breaks up into a lithium and a hydroxide. Once again, remember, OH is the polyatomic ion, so we're really breaking it right there. This one I didn't even bother to put the line because the nitrate's already in parentheses. But there's 3 of them, right? So we're going to end up with 3 lithium ions. And once again, in the interest of time, I'm just going to tell you, lithium's in column 1, so it gets a +1 charge. And we just saw that makes sense because hydroxide has a -1 charge. We just saw that. And so because there was a 3 in front of it, we also say that there's 3 hydroxides. Right? So notice that as far as my reactants are concerned, I've broken them up into the aluminum nitrate and lithium hydroxide. I end up with 1 aluminum ion, 3 nitrate ions, 3 lithium ions, and 3 hydroxide ions. And on the right side, this is also aqueous, lithium nitrate. And just like lithium hydroxide, lithium nitrate, we break it down right there. Right here, we didn't have the parentheses around the polyatomic ion, the nitrate polyatomic ion. But we can tell the first element is a metal, so we separate it from the rest. And the rest is your polyatomic ion. There's 3 lithium nitrates, which means that there's 3 lithiums. 3 lithium ions and 3 nitrate ions. Okay. And then that's going to go ahead and take us to the last one, aluminum hydroxide. Aluminum hydroxide is a solid, so therefore we don't have to break it up. Yeah. Aluminum hydroxide is solid, so we keep it together. Solids, liquids, or gas. Sometimes you see liquids, sometimes you'll see gas. Like sometimes you form water in these. You keep them together. You don't break them into ions. Only aqueous substances. Step 2 then. Step 2 I think is the hardest. That's why I had you guys do the worksheet yesterday. So step 1, balance the equation. Step 2, break up all the aqueous substances into ions. Step 3, cancel out spectator ions. In other words, cancel out what you see on both sides. Here's 3 lithiums and 3 lithiums over here. There's also 3 nitrates here and 3 nitrates here. 3 hydroxides here, but no 3 hydroxides on the side. An aluminum ion, but no aluminum ion here. Once again, this is aluminum, but it's part of the solid substance. So we consider it differently than aluminum ion. So we cancel out the 3 nitrates. We cancel out the 3 lithiums. And that's step 3. Last step, just rewrite what's left over after all the wreckage, after you've taken out all the ions. So there's an aluminum ion, plus 3 charge. There are 3 hydroxides. And that's going to turn into aluminum hydroxide. All right, that's all that's left. So this is our net ionic equation from this complete complete balanced chemical equation. This is a molecular balanced molecular equation. This is a net ionic equation. Sorry, drew a blank there a little bit. And once again, if you want to put what states of matter these are in, this aluminum ion came from the aluminum nitrate. That was aqueous. The hydroxide ion here came from the lithium hydroxide, which was aqueous. So I put that as aqueous. And the aluminum hydroxide, we didn't separate out because it was solid. So this is what you would put as your answer. Okay. All right, good. All right, I'm going to do one more because I want to point something out. So I need to, I guess, open up another of these. Do this here. All right. Let's say we had a something like this. Okay. And all right, so let's say this here is aqueous. I'm sorry, that looks terrible. Try that again. Aqueous. Well, better. The iron is solid. FeCl3 is aqueous, and the copper is solid. Okay. All right, so let's say we have this equation right here. So once again, 4 steps. Step 1, balance the equation. There's 1 copper, 1 iron, 1 iron. But there are 2 chlorines here. There are 3 chlorines on this side. So we still need to balance the chlorine. So if I go ahead and put a 3 in front of here, it's going to balance out. It's going to give us 6 chlorines. And if I put a 2 in front of this one right here, it'll give us 6 chlorines also. So we'll balance out the chlorines by doing that. We unbalance the irons and the coppers. But the irons and the coppers are pretty easy to balance because they're by themselves. So since we had 3 CuCl2, we need 3 Cus over here. So that there's 3 coppers on each side. And since we had 2 FeCl3s, we're going to need a 2 in front of the Fe on the left, so that we end up with same number of Fe's. Now it's balanced. Okay. Now it's balanced. Step 2, break these up into their ions. And their ions here would be, and I'm going to go a little faster because we've seen a couple of samples already, and I want to get to something else here. So I'm not really showing you how to do this at this point. Breaking up into ions, I'm going ahead and get into another point later on. All right, so 3 CuCl2s break up into 3 copper ions. Should be U. That's copper 2 chloride. And 6 chloride ions. And then the iron remains as a solid. And then on the right side, the 2 FeCl3s break up into 2 iron ions. Sorry, it should be 2 irons. 2 iron ions, 2 iron 3s, because it's Cl3, and 6 chloride ions. and then the 3 coppers. Three coppers. Okay, so the 3 copper chlorides turn into 3 copper ions and 6 chloride ions. The iron just remains the same. The 2 FeCl3 breaks up into 2 iron 3 ions and 6 chloride ions, and the 3 coppers remain the same. Cu, not a Ca. The feeling that they start looking toward like each other. All right, the third step is cancel out spectator ions. This is what I want to get to. There's 6 chlorides here, 6 chlorides there, so they cancel. Now, a lot of people here do this. They see copper here, copper there. They cancel them both out. Iron here. They cancel them both out. And then nothing remains. Okay? Which actually is a possibility in some equations. If everything's aqueous, basically everything breaks up into its ions, you're going to cancel everything out and you'd call it a no reaction. That's not the case here. The reason for that is this. This copper right here is a copper ion. This copper over here is not. So if you look at this charge right here, the +2 is different than this one over here, which is neutral. It's solid copper. It's a piece of, if you had a piece of copper, if I had a copper pipe, it's different than copper ions. So we don't cancel those out. Same thing with the iron. This iron here is neutral. There is no charge to it. And this one right here, it's a +3. Okay, so we don't cancel them out. The only way you cancel them out is that if they have the same element and the same charge. Hey, there's sometimes when you have an iron 2 turning into an iron 3. You don't cancel those out. You only cancel them when they're identical. So these guys we don't cancel out. We're just going to go ahead and write it as 3 copper 2 ions plus 2 iron atoms. No, they're not. This is not iron atoms. Iron ions. They're atoms. Going to form 2 iron 3 ions plus 3 copper atoms. Once again, if they're neutral, they're atoms. They're not ions. They got a charge. They're ions. And then once again, we can go ahead and put the states of matter. The copper ion came from the copper chloride, which was aqueous. Whatever the state of matter was there, you can put it for down here. The iron was solid. Over here, the iron ions came from the iron chloride, which is aqueous. And over here, copper is solid. Okay. And so this would be our net ionic equation for this one. Really what happened was we call this oxidation reduction, where you change the charge on different atoms. I mean, there's actually a whole chapter at the end of the book on this. I don't know if we'll get there. When you go from copper at +2 state to copper neutral, it is gaining electrons. So it's undergoing a process called reduction. And when the iron goes to iron +3, it's in order to become +3, it's losing electrons. And so in order to lose electrons, it undergoes a process called oxidation. So one of these is being reduced, the other one's being oxidized. You won't be tested on that right now. I just thought I'd kind of throw it in there, especially if we don't get to covering it at the end. But the key is here that this is at one call it oxidation state, one charge, get into another oxidation state or no charge. And the key is understanding that you cancel out the chlorides because they're the same element with the same charge, but you don't cancel out the two atoms of the same, or 2 particles of the same element that have different charges. They're different. You don't cancel those out. Okay. All right. So I hope this is helpful for your worksheet. This is what you're going to be doing on the assignments on the worksheet. All right. If you have any questions, let me know.